We good on the sound? Cool. Okay, so today I want to start by telling you something about dependent types. So the plan is that this morning I'm going to tell you some of how I think about dependent types, and then this afternoon Bob's going to tell you some of how he thinks about dependent types. And then starting tomorrow, Edwin Brady's going to tell you a lot about how he thinks about dependent types, and maybe there'll be some overlap between some of the stories, or maybe not, we'll see. But it's kind of a simple idea that can be expressed and understood in lots of different ways. So I want to start off by motivating dependent types by proving an extremely deep theorem in mathematics, which is that every natural number is either even or odd. And you may not be convinced this is true a priori, but we'll get there. It may take the whole lecture. Okay, so how do we prove this? Can anyone suggest a proof technique that might apply to this problem? Induction. Okay. So formally, we should say this as for all numbers n, either n is even or n is odd. And then we can say that we're doing this by induction on n. And what do we do if we do an induction on n? We have a case for 0, and we have a case for 1 plus k. And in the case for 0, what do we need to show? 0 is even or 0 is odd. Well, why is that true? Because 0 is even. Okay, why is 0 even? Well, we didn't define what being even means, so it's hard to say. But we could define n is even to mean there exists an x such that n is equal to 2x. And we could define n is odd to mean there exists an x such that n is equal to 2x plus 1. That's assuming we have some notion of equality and multiplication by 2 and addition with 1 to use. And then how can we see that 0 is even? Because 0 is equal to 2 times 0. Therefore, there's some x such that 0 is equal to 2 times x. Okay? All right, what about the case for 1 plus k? What we need to show, actually, let me write it this way. What we know by the inductive hypothesis is that k is even or k is odd. And what we need to show is that 1 plus k is even or 1 plus k is odd. Right, because if we're doing an induction on n, then we get that the predecessor is either even or odd. And what we show then is that the successor of the predecessor is either even or odd. Okay, so how do we fill in the gap here? Okay, so based on this, we get two cases. Let's say A and B. And in case A, we get that k is even. And in case B, we get that k is odd. And then we need to show this or this. Well, suppose k is even, then where are we going with this? We're trying to get that 1 plus k is odd, relying on your mathematical knowledge that the successor of an even number is odd, right? Not even. Of course, we could have tried to show the other thing, but hopefully we'd get stuck. So how do we get there? What does this mean? This means there exists an x, or let me call it y, such that 1 plus k is equal to 2 times y plus 1. And what does this mean? There exists an x such that k is equal to 2x. So what do? Take y to be x, right? And then add 1 to both sides of the equation. Good? Okay. And in the other case, if k is odd, that means there exists a y such that k is equal to 2y plus 1. And we want to show that 1 plus k is even. And what does that mean? There exists an x such that 1 plus k is 2 times x. And so what do we choose x to be? Yeah. If you take that to be y plus 1, then 1 plus k is equal to 2y plus 1, which is 2y plus 2, by adding 1 to both sides of that. Okay? So you can see that what we're doing here is sending that to that and that to that, if you look at how the case analysis goes. Good? Okay. So what we're going to do is we're going to introduce dependent type theory as a formal system in which we can do this proof. Okay? So what do we need to do this proof? We need to understand this bit and this bit and this bit and this bit and this, right? The ingredients here are for all and natural numbers and or and exists and equals and the ability to write 2 times as a function and things like that. Okay, so we've been developing lots of types over the course of the last few days. And what we're going to see is that these are just some more types. And then once we have those types, we'll go back to how we translate this proof into that formal system. And the cool thing that's going to happen is that there's an analogy where the logical connectives correspond to types, and the proofs of those propositions correspond in a certain sense to programs or terms that have those types. Okay? So how many people have seen some version of props as types or Curry-Howard or something like that? Okay, so I won't really dwell on that since people seem like they're on top of that. But if we just go through how it works in this particular case, what I do want to do is go over sort of using the machinery we've developed over the course of the week, what is a for all type and what is an exist type, and what is natural numbers and what is equality and stuff like that. Okay? So the first thing we need is let's talk about the for all n in n. So how does that work? So what we're going to do is to move from the simple types we've been talking about so far this week to what's called dependent types. And the idea with dependent types syntactically is that we'll have the notion gamma proves A is a type. Okay, so I'm going to switch from tau, which we were writing for types in the simply typed case, to capital Roman letters ABC, just because that's the more common notation in dependent type theory. But everywhere where I say A, B, or C, just think tau sigma if you're more used to that. And then we'll have a judgment, gamma proves A colon A, where A gets to depend on gamma, which means mention variables from it. Okay? So for example, we can have the idea that in the context x is a nat, even of x is a type. Right? We needed that when we said every number is either even or odd. We needed the idea that we could talk about a number in a type. Okay? So that'll just be mentioning a variable from a context. And along with these, we're going to need to know, for example, some notion of when in a prime. Okay, so other notation switches. What we've been writing as E for programs and tau for types, people usually use lowercase letters that correspond to the uppercase letters there for terms that have that type. Okay, so I could have written this gamma proves tau is a type, and gamma proves E colon tau to match the notation from the last few days. But so this is going to be some notion here of what's called judgemental equality of terms. So this is a judgment that says when are these two terms, which are presupposed to both have type A, equal. And it's pretty subtle what this should mean. There's a lot of points of view on it. It's not at all a fixed thing. It doesn't have like a universal property or something like that that defines it. But the way to think about it is, for example, maybe it's the case that 2 times x plus 1 is judgmentally equal to 2x plus 2, the fact that we used somewhere up there when we were checking that any successor of an odd number is even. Right? So you can think of this as including some basic computation steps. Okay, so that's the setup. We have being a type, which can mention variables. We have being an element of a type and being equal elements. And this induces a notion of being equal types, but we can kind of slip past that for a second. All right, so now let's talk about for all. So in dependent type theory, there's a type pi x colon a dot b, which is a type under the assumption that A is a type, and assuming x has type A, B is a type. Okay? So this is very similar to the rule for all that we had yesterday, right? We said for all alpha tau is a type if, assuming alpha stands for a type, tau is a type. Here what we've got is assuming x stands for an A, B is a type. Okay? So you can imagine parsing something like for all x colon n even of x. I mean, that won't be true, but it's a well-formed type. We could ask the question, right? So this will correspond to pi x colon n even of x, because we're going to parse the for all quantifier as a pi type. Okay? And so then the thing to observe is that to show this is well-formed, what you show is assuming x is n, even of x is a type, and we'll get to the definition of even, but that will turn out to be a type when x stands for a natural number. Okay, so you see what's going on with the formation rule here? Questions on that? Yeah?
So it's a type level even, right? Not like a value level even?
Yes. So the even of x is a type. We'll define it in a second. I mean, we'll define it essentially by that formula. There exists an x such that n is equal to 2 times x. Yeah? It's a good question. Let me get through some of the rules for judgmental equality, and then we'll see. Yeah. Okay, so now what should an element or a term or a program that has type pi x colon a dot b be? Right, hopefully we're getting pretty good at seeing that things that look like ferals or arrows or something like that will have some kind of function as an element. Okay. So the elements of a pi type are functions. And under propositions as types or Curry-Howard, what we're saying is that a pi type is how we'll write a feral, and a proof of a feral will be a function. Okay, we think of a proof of a feral as a function that, given a proof of A or an element of A or something corresponding to A, gives you an element of B. Right? Just like yesterday when we saw that an element of a type quantifier for all was a function that took a type. Here we go. Okay, and then the dual thing will be that if you have f, which is of type pi x colon a dot b, and then you have a as in a, then function application of f to a has type b, except there's a little bit more to say, just like there's a little bit more to say when we had the for all quantifier in system F yesterday being applied, right? Because what we have here is not a function from A to B, but a function that for each thing in A delivers a B for that thing. Therefore, we substitute A for X and B in the conclusion. Okay? So if I had my proof up there, which said pi x colon n even of x or odd of x, then I could apply p to 7 and get even of 7 or odd of 7. Right? When I apply a dependent function to an argument, what I get is the range of the function for that argument. Good? Okay. And so now we can talk about the judgmental equalities, which are that we'll say things that look like beta reduction and eta expansion, but the way I'm thinking about these, at least for now, is they're just sort of formal equational axioms that we place on these terms. Yeah?
In the very last substitution,
Yeah?
how do you know which x is supposed to be substituted?
So I should have maybe said this more clearly, but this x here is bound in B, which is what this kind of judgment is supposed to indicate to you.
No, but how aren't there many different x's bound in B?
So like in our example, x colon n says that even of x or odd of x is a type. So x there and there both refer to that. And so then you replace all of them with 7 because you get that 7 is even or 7 is odd. So all occurrences of this variable here get replaced. Right? If I had a different statement, which was like, for all x and y, x is even or y is odd, or something like that, then this would be 2 pi's in a row. And when I applied this, I would replace this if I applied, so suppose I have a g of that type. When I applied g to 7, what I would get is, for all y, 7 is even, or y is odd. Okay, so you only replace the bound variable for that function. Yeah.
So the variable is bound in the context or bound by the type?
Well, so the general, I mean, so the general way that everything works, if we even just go back to like lambda x dot e having type tau1 or tau2, is that in the syntactic term, it's bound here, right? And then in the typing judgment, you pass to a judgment where you think of the variable as being bound there, right? So like when you type check a lambda, you pass to a judgmental state where the variable is bound by the context. But then in the lambda itself, it's bound by the term. There was more questions, yeah?
Just to clarify, even 7 or odd 7 is still the type.
Yeah, we haven't defined it yet, but it will be, yeah. Yeah.
So can you find x in both the type and the term at the same time?
Yeah, so that's a little bit of a cheat. So if you wanted to be more official about it, and you could say that lambda x, where x is bound in B, has type pi y, where y is bound in big B, if maybe z says that B with z for x is capital B with z for y. So there's a moment here where you have to coordinate the variables between those two occurrences. But usually what we do is we cheat, and we just say, by alpha conversion, I'll assume that they're the same when I write the rule there. Yeah. Sorry? So, no. So the way that I'm doing things, there's a separate judgment, 1, that A is a type, and 2, that A is an element of A. So we can introduce a universe in a little bit, which will turn this into being element of a type. But here I think of the judgment of being a type as being just a separate judgment from being an element of a type. Well, I mean, this is a variable standing for an A, not a variable standing for a type anymore. No, it's a term variable. I mean, it's just like the normal lambda variable, right? It stands for a value or something. Okay? Good? Okay, so let's see, where was I going with this? So now we're going to have some judgmental equalities, like in context gamma, lambda x dot A applied to, or let me call it lambda x dot B applied to A will be judgmentally equal to B with A for x in the type B with A for x, assuming x colon A, B is B, and A is A. And we might say that in the type pi x colon A dot B, f is lambda x dot f applied to x, assuming f had pi x colon A dot B. So this is the beta rule, or the eta rule, or the thing that arises from cut, or the thing that arises from identity expansion, stated as equational axioms about these terms. Okay? So there's a subtle point, which Bob will come back to this afternoon, I think, about these look like beta and eta. In particular, that looks like beta. But a priori, it's not really the same as an operational step. Okay, the right way to think about a formal dependent type theory like this is what we have is a collection of terms and a collection of equational axioms on them. And we're picking them in a suggestive way because we understand things about logic and computation and proof theory and stuff like that. But like, to some extent, this comes back to the question of like what judgmental equality is. Judgmental equality could be anything, right? We could put in some equations that don't have any particular computational meaning. That would be fine in a sense. We'd still have a perfectly good system with judgments like this and this and this. And you can do things with that. And for certain applications of dependent types, you might want things like that. But if you think of these, like, we might come up with these motivated by computational concerns or by cut and identity, but there's a little bit of a gap between that and saying these are actually programs and that's actually an operational step and stuff like that. Okay, so just keep that distinction in the back of your mind as we go through the day. Okay, so we good on pi types? Good? How many people have seen like pi sigma identity type rules before? Okay, so many people, but not everyone. So let's quickly do sigma. Okay. Okay, so for sigma, the corresponding idea is that sigma x colon a dot b is a type under the same conditions that pi was. A is a type, and assuming x colon a, b is a type. And then the introduction form is pairing of an a and a b to get a sigma x colon a dot b. And what do you need to pair together? You need to pair together an a and a b. Well, if we were just making a regular pair, we would pair together an a and a b to get a pair of an a and a b. If we're making a dependent pair, then what we do is we pair together an a and a b for that a. Okay, so if you think back to the pack rule from yesterday for existential types, it's exactly the same idea. You pick a representation of an a, and then you pick a b for that. And then, unlike existential types, what we're going to have is if we have a pair of type sigma x colon a dot b, then what we get out of it is the first projection of a, p, which is an a, and the second projection of p, which is a b, for the first projection of a. So this is a very strong existential because you can project the witness. Okay? So what this is saying is it's an existential. There exists an A such that this holds, but we're somehow committing to the fact that the witness for that existential is really sitting right there, and we can get our hands on it whenever we want. Okay? The elimination rule that we said yesterday for polymorphism, which was exists alpha tau arrow sigma, is the same as for all alpha tau arrow sigma, doesn't have this kind of projection, right? There's no way to take an existential like this and get the type part out of it. All you can do is write some other code that works for all types. Here we can actually get the A out of there, which is nice because then, for example, we can define the non-dependent pair A cross B to be the non-dependent sigma A and B. Okay, so the cross type that we've been talking about since Monday is just a sigma type where the bound variable there happens not to occur in B. And dually, I should have said this on the other board, we can define a function type A arrow B to be the pi type where the variable happens not to occur. So sigmas and pi's, we talked about them as functions and pairs, generalize the function and pair types that we've seen so far. All right, and so then we'll have corresponding, I'll just write the quick form, which is that we'll have first of AB is definitionally equal to A, and second of AB is definitionally equal to B, and anything of type sigma is judgmentally equal to the pair of the first projection and the second projection. And these are really all typed equations, and you can work out the fact that they type check from what we've said so far. Okay, so these are not like untyped reductions or something like that. These are equational axioms for a judgment of equality between typed terms.
What's that say in the substitution for the sigma?
This? Yeah, first of A. Or sorry, first of P. Yeah. Sorry. Typo. Right, so if P is a proof of a sigma, then the witness is the first of P. And what you know is that B holds for the first of P. Okay? So let's do an example now. So how do we define n is even? What should the existential symbol turn into? Sigma x colon natural numbers, such that n is equal to 2 times x. Okay? So we still need to define the equals and the nat part, but at least we've got the sigma part. Okay, so what does this say? This says to prove that something is even, what we do is we give a number and we show that the number where what we want to show is even is equal to the doubling of that number. Okay, that's the interpretation of an existential that we have here. We give a number and we show that equation, right? This consists of a pair of a number and a proof of an equation. Right, which is what we did up here kind of on the sly. We said to show that something is even, we take x to be y plus 1 for that y. And then we showed this equation by, I said out loud, this equation holds, and you were like, yes, it does. Okay? So we didn't really write that out explicitly, but that's what was going on. All right, so we've got sigma types. Okay, so now natural numbers. How does the type nat work? Well, n is a type outright. 0 is a number. If n is a number, then successor of n is a number. And we'll have the recursor, which says that if I'm trying to prove C from n, where I know that n is a number, and I know that C is a type, then what do I have to do? I have to show that I have a, let's call it branch 0 for, okay, let me rename C to B, just so the notation matches. I have a branch 0, which is a B, and I have a, for every x in n, for every r in B, branch 1 is a B, and then based on all of that, the rec of B0 and xr dot B1, I get a B. Okay, so do you parse that? Did I get it right? Is that, hopefully that parses as the recursor that we talked about and you played with in the homework a few days ago. Right? What I do is I show B, and then I give a B, and then I give a B assuming a number and a b, where this is the predecessor and the recursive call, and then I get a b. So our basic principle here is structural recursion on numbers. Yeah. Mm-hmm. Depends what you mean. So one thing that we don't want out of so if we want types to be proofs of propositions, like we were gunning for on that board, then we don't want recursive types in their full generality, because we saw yesterday that recursive types in their full generality give you general recursion. And if you think about what general recursion lets you do, if you think about the fixed point, right? The fixed point lets you write fix x colon a is x, which has type A, because assuming x is A. Okay? And so if you read that logically, that's saying, I can prove any proposition by writing an infinite loop. Okay? So if what you're interested in using dependent types for is doing behavioral program verification about programs that may not terminate, so when you look at the work on dependent types in Haskell or something like that, that's sort of what they're gunning for, then it's fine to have recursive types and dependent types. So in a certain sense, yes. But you would be mad if I proved this theorem by saying every number is even or odd because infinite loop, right? Like that wouldn't be what you had in mind as a mathematical proof. Okay, so it depends what you're trying to use the dependent types for. So because of this, the basic system of dependent type theory is usually set up like this. Okay, good? Yeah.
For the typing for the judgment equality,
Yeah.
is it the equality itself has the same type as each term?
It's that each of these terms, each side is supposed to have the same type.
And the equality itself has that type also?
No, the equality itself is a different judgment. So the equality doesn't have a type. So like this colon is just notation, right? Yeah. So like,
Or each one of those has type?
yeah.
Okay.
So like I could have written that with a different symbol, like A is equal to A prime as A's or something like that. But yeah.
So yesterday we derived a lot of our types like NAT from recursive types.
Mm-hmm.
Are we baking them into our logic now?
So for right now, I'm baking in NAT. So instead of recursive types, you can add things that are called inductive and co-inductive types. And this is the kind of corresponding way to get a general mechanism that includes NAT and list and tree, blah, 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 blah. You just have to pay a little bit closer attention to what's going on. You don't, so basically, you're allowed to have things like NAT and list and tree, but you're not allowed to have things like the recursive type such that D is isomorphic to DRD. Okay, because that would give us general recursion again. Okay, so it's a restricted fragment of the general recursive types we studied yesterday that makes sense if you want programs to terminate. Yeah?
All right, in the last part of the structural recursion,
Mm-hmm.
in the top, you have R, which I think is the recursive call.
Yes.
That's a B.
Mm-hmm.
Doesn't have to have some function.
Yeah, so like, I mean, B itself might be a function if we're,
But it, okay, but in red, inside red, you have, I can't really use that. Right?
oh, so let me write it bigger. So this, so B1 has X and R free in it. And then what we always write down here is dependent on X and R, B1. So that's really just putting B1 as part of the syntax. Yeah. Good? Okay, so now we're in a, okay, so like I'm going to defer the question of what exactly this symbol means. But absent that, we're in a position to start thinking about what it would look like to do that, right? So what we've got now is the ability to parse the thing we said at the top there. As the following formula: pi x colon n even of x plus odd of x. Okay, so I didn't define plus, but it's just the rules for coproducts that we talked about a couple days ago. Okay, so the plus type, the or, will just be the coproduct type, and it'll have in left and in right as introduction forms or values, and recursion. Well, what is recursion for coproducts? It's case analysis. Okay, so just think about the rules for coproducts that we've set up already. That's our plus. Then we'll define even of n to be, even of n to be there exists an x such that x is equal to n is equal to 2 times x, and odd of n as there exists an x such that n is equal to 2x plus 1, where you can imagine how to write the double function 2 times blah by recursion on numbers, sending 0 to 0 and successor to double successor, right? I think we talked about that in one of the homework exercises. Yeah? So, yes, so coproducts, right? So like the thing I sort of said out loud but didn't write is A plus B is a type, assuming A and B are each types. And if I have A and A, then I have in left of A, which is A plus B, and dually for in right, and then a map out of A plus B into C. I'll do the quick version. Consists of a map from A into C and a map from B into C, right? Which is like a very abbreviated way of writing a case analysis, right? So really, it's like the full case analysis rule. Mm-hmm. Mm-hmm. So like sigma is sort of, in terms of the proof terms, naturally a generalization of products, right? So, yeah. Yeah, I mean, I can't think of exactly what like a x colon A plus dependently plussed with B would be. Actually, I can think of something it might be, but it's a little bit far afield. Yeah, okay, so like that, yeah. So like you could imagine what that would be, but it's, yeah, I'm not totally sure. Okay, question mark. Right, but like that's definitely not a standard type. Yeah. So we put in coproducts just as we usually put them in.
Could you somehow build coproducts from dependent sum by using the first thing of this sort of hat?
Yeah, exactly. Yeah. So part of the reason why dependent sums are called dependent sums is that you can in fact just put in Booleans, not arbitrary coproducts, and then define A plus B to be sigma x colon 2. If x, then A, else B. Where here, we're using something we haven't talked about yet, which is the ability to discriminate on a value, and based on that discrimination, choose a type. Okay, and so if you do that, you can implement coproducts as a pair of a tag bit and a data. And so then you don't need to make them primitive. But you sort of do need to make them primitive because you need Booleans to get started. So you're at least adding in one instance of a coproduct as a primitive. Okay, good? Okay, so now we've got our type set up. How would we prove it? We would start with lambda n colon n. And then what we want to do is we want to discriminate cases on 0 and successor and get an inductive hypothesis over here. Well, that sounds like rec, right? So we would do a rec to prove, right? Here what we're trying to do is we're trying to show n is even or n is odd. And so we would do a rec on n. And then that means we have to give, if I write it in sort of a nicer notation, a case for 0 and a case for 1 plus k with a variable standing for the recursive call. All right? And then the idea is somehow in this case, what we said in the proof is that we need something that says that 0 is even, right? Well, what does 0 is even mean? It means there exists an x such that x is equal to 0, keep getting it backwards, is equal to 2 times x. And so somehow here, using our rules for sigma types, we should be able to say, take this to be 0, and then if we take 0 for n here, the second premise is 0 equals 2 times 0. Well, that should be true by some sort of reflexivity principle for equality, right? Because we can imagine, well, when you define the doubling function by induction on numbers, double of 0 is just 0 by reduction. And I didn't say it, but we'll have that rec of b0 x dot r dot b1 on 0 is judgmental equal to b0, and rec of stuff on 1 plus k, I guess I'm being inconsistent about whether I'm writing this as 1 plus or successor, is equal to b1 with k plugged in for x and with the recursive call plugged in for r, right? So just the step rule that we had in Gödel's T way back on Monday. Yeah. Good question. Well, what we need here is that a way of talking about equality of open terms, right? Because if you think about what we're about to do in the next step, right, then we're going to end up trying to prove something like y is equal to 2 times x plus 1 or something like that, where we have variables y and x, right? We're going to need to make statements about things with variables. So what we've been talking about so far is operational semantics on closed terms, and then maybe lifting that to some semantic contextual equivalence, logical relations kind of notion of equality of open terms. But here, reasoning about open terms happens all the time, because in context, we'll talk about even of x, where x is a variable. And so judgmental equality is a formal notion of these two terms are equal. Okay, these two open terms are equal. Okay, so did we finish this case of the proof? Assuming that there's a reflexivity that says 0 equals 0, and that everything kind of respects judgmental equality. So one way to phrase that as a rule is that if A has A, and A is a judgmentally equal type to B, then A also has B. Okay, and you can imagine that when you have an equation type, which we haven't talked about yet, that says that, right, so if I want to show that reflexivity has type 0 is equal to 2 times 0, then by this principle, it suffices to say 0 is equal to 0. Okay, and that's because 2 times 0 will be judgmentally equal to 0. And that's because that's just unfolding the computation of the doubling function as we defined it way back when. Yeah?
Which part of what you wrote here is now part of the expression?
So the expression, let me erase the scaffolding. the expression as opposed to the like stuff off to the side, which was helping to type check the expression, is that. Yeah.
So in a proof of system, is it enough to write something like that, or are we responsible for showing that that eventually implies what we have said it does by working on it?
Another very good question, and it depends on what kind of proof assistant you're working in. Yeah. So in many proof assistants, it's set up so that there's a distinction where you write the term, and from the term you can decide whether it has a type. Well, you write a type and a term, and you can decide whether a term has a type. In other kinds of proof assistants, the fact that something has a type is a semantic property that you have to prove. Yeah. So that's a, yeah. Okay, so we wanted to show that something was even or odd. Well, the elements of even or odd are the elements of a coproduct. So we need that. Now are we done? I mean, with this case. Really? So let's look at the typing for the recursor. What it says is, to produce a B, you give a B and you give another B. What's the thing we're trying to produce in this case? We're trying to produce, for this variable n, something that has type even of n or odd of n. What we produced was something of type even of 0 or odd of really anything we wanted. Right? But in particular, odd of n. Odd of 0 or odd of n or whatever. Is that good enough? Morally, yes. Formally, no. Right? Somehow, we haven't yet captured how a proof by induction was supposed to work. What we said was, we can write a function by recursion that produces a B and assumes a B and produces a B. But there's nothing about this rule here that says that in this branch, n becomes 0. And in this branch, n becomes 1 plus k. Right? When we did our proof by induction, we said we have a case for 0. And if we're showing for all n blah, then in the case for 0, we show the predicate for 0. And in the case for 1 plus k, we assume it for k, and we show it for 1 plus k. Right? Somehow, this rule doesn't capture that yet. Okay? So the thing we forgot to do is to generalize recursion to induction. And what that means is that the type that you prove gets to depend on the thing, a variable standing for the type that you're proving something about. And then in the case for 0, you show it for 0. And in the case for successor of, let's call it k to match the other proof, you assume it for k. And you show it for 1 plus k. Okay? So recursion is the simply typed case of induction. In general, when you're writing a dependently typed function like this, we need not just to do recursion, but to do induction, at which point here what we need is not to show even of n plus odd of n, but to show even of 0 plus odd of 0. Okay? And then with that, we can do the rest of it. So this will look like what we said on the board. case on the recursive call, if it's in left, then it's going to contain, let's see, if it's in left, then it's going to contain a x and then a proof p, which says that k is equal to 2 times x. And then in the case where k was even, what did we do? We said, what I'm going to do is I'm going to show that 1 plus k is odd by giving back an inright, right? Because we showed that from k being even, 1 plus k is odd by switching the in left to an inright. And then here we take the same witness and a slightly adjusted proof. And then in the inright case, what we did was we said we get x and p, which is a proof that k is equal to 2x plus 1. And then we switch that to an in-left case with x plus 1, and then the slightly adjusted proof that we did down here. Okay? So if k is, so r here is what says that k is even or odd. In the case where k is even, we get an x and we know that k is 2x. In the case where k is odd, we get an x and we know that k is 2x plus 1. If k is 2x, then the same x shows that 1 plus k is equal to 2k plus 1. So we know that 1 plus k is odd. And here, the x plus 1 is the witness that 1 plus k is equal to 2 times x plus 1, which is equal to 2x plus 2. Okay, so I'm leaving out the manipulation of the equalities here because we haven't talked about the equality type yet, but that's the logic of it. Okay, so if we take our proof that we did at the beginning and interpret it, interpreting the logical connectives as pi and sigma and coproduct and stuff like that, then if we squint at it, we can see this as a program. And in a sense that I'll talk about in a second, it's not necessarily formally a program. We'll get to that this afternoon too. But if you squint at it, you can see it as a program. And so the question is, what did we compute? What does this program do?
I don't have the answer to that, but
Okay.
I have a question about that 1 plus k equals 2x plus 1.
Yes. Yeah.
Where did the x come from?
So sorry, there was a little glib here. So formally, this is an element of even of k, right? And even of k is a sigma type, right? Even of k is defined to be a pair of an x with a proof of an equality, okay? So what I did, sorry, I should have been more formal about it, but what I did was I pattern matched that sigma as a pair, which you can translate to x is the first projection of this, and this will use the second projection of that. So in most proof assistants, you can either use a sigma by first and second projection, which are kind of the fundamental rules, or you can pattern match them when they're inputs to a case analysis. And that's a little bit handier here. So I'm breaking apart the fact that, let me type check it. I'm breaking apart the fact that I have in left of x comma p, which says that k is equal to 2 times x, is an element of even of k plus odd of k, which is equal to there exists an x such that x is equal to 2k plus some other stuff, right? Because that's what even means. And so the in left matches the plus, the x is that x, and the p is the proof of that equation. Okay, so back to the question of what are we computing?
Are we computing that, well, the truncated division by 2 basically?
Yeah, so it's not even truncated. It's division with remainder by 2. Okay, because when you put in a number, right, what you get is either half of that number or half of that number minus 1. And so the in left or in right is telling you the remainder. Remainder 0 for in left, remainder 1 for in right. And the number you get out is telling you the div by 2. So interpreting the proof that every number is even or odd constructively is computing the division by 2. You think of that as the witness for the division by 2 is that. Okay, is half of the number. All right? So when we adopt this point of view that proofs are programs, for alls are pies, exists are sigmas that have data that are witnesses that are sitting right there, sums are, ors are coproducts, we can get information out of all of these types. Okay? And so I think, yeah. Yeah, so this is all an intuitionistic dependent type theory. Okay, so Edwin's going to be following up on that kind of thing as we go on over the course of the next set of lectures. And you'll be using Idris to do some programming in this sort of style where you're doing this sort of thing. Okay, so let's see, how are we doing? Next things to say, okay, let me just quickly do a few quick hits about different kinds of things, just so you have a hook when you run into them later. So we didn't talk about what it means for x to be equal in y in A, in the sense not of the judgmental equality there, but in the sense of the type that we used, A equals B in A, which is a type which is well formed. Well, let me write it over here. When both A and B are elements of A, and this is called the identity type, or sometimes the equality type, right? And notice that when we defined even of n to be there's an x such that n is equal to 2x, this thing has to be a type, not a judgment, in order for that to make sense, right? You can't take the sigma of a type and a judgment and get a type. You can take the sigma of a type and a type and get a type, okay? So we somehow need a type of equalities in A. Well, here are the rules. Reflexivity is an equality A in A, if A is in A. And it's a little bit complicated. Let me write it as a function instead, since I think that's a little easier to parse on a first go. Suppose we have C which is dependent on x. And suppose we also have P, which says that A equals B. Then from this, we get a function that's called transporting in C along P, which says if you can get C for A, then you can get C for B. Okay? So what this is a way of saying that if you have an equality, then so suppose that A is equal to B in the sense of this identity type, then if you can make a C for A, you can also make a C for B. Which makes sense because somehow we've said A is equal to B, which means anything you can do with an A, you can also do with a B. Okay? And so you can write that out as an inference rule and then turn it into an induction principle instead of a recursion principle, and that gives you the elimination rule for the identity type. Yeah? Oh, sorry, yeah. Typo. Okay, so that's how the identity type works. And using that, for example, from this principle, you can define something that says if A equals B, then it's also the case that f of A equals f of B, right? So we used that somewhere in our proof before to say that, so this is assuming that f is a function from A to B, and you have an equality in A, you get an equality of B, right? Somewhere in the logic that we did before, we went from the fact that x equals 2k, or k equals 2x, we needed to get from that 1 plus k is equal to 2x plus 1, right? How do you get that? Where does that come from? Why do you know that if you have a function and equals, then you get equals? Well, that comes from this principle here of transport. Okay, so you can write this out as a particular instance of that and prove that. Okay? So I think we've now successfully written rules for everything we need to type check that proof that we had on the board. And so if you get a chance, you can maybe do it in Idris over the next few days, or grab a friend who knows Agda or Coq or something like that and try to do it there. It's a nice first example. Yeah?
So is that transport like what's called congruent in Idris, or Kong? Or?
It's not exactly Kong. I think it's probably called substore or something like that. What do you call transport? Replace. It's called replace in Idris. Okay. Yeah. Okay. So now we've got 10 minutes. So I just want to kind of pop up a little bit and talk about sort of what you can do with this sort of thing. So we've got a bunch of rules on the board, right? We've got rules for pi and sigma and identity types and natural numbers and coproducts. And personally, right now, I'm thinking of this as a formal system. Okay? We're talking about a formal logical system where we have some syntax and some equations and some judgments, and we construct elements of those judgments. Okay? And then there's different ways you can go with this formal system. Is there Yeah, let's save details of transport for the hands-on session, just because it's. Yeah. So it's really the elimination rule. It's a kind of function-y way of writing the elim rule for this type, but we'll have to do a few examples. We can do it this afternoon. Yeah, I want to just. Yeah, and transport's the elim. Yeah. We don't yet, but we could define that too. Yeah. So like transport, and then you want to make that into an induction principle. Okay, but just popping up for a second in the last 10 minutes here. So we've got a formal system. Okay, and there's different directions you can go with a formal system. So we've written things that look like beta and eta, right, reduction rules, as part of our definitional equality. That doesn't make definitional equality into a computation system. What you can do, if you want, is show that this formal system has a computational model. And Bob will talk more about this afternoon. So this means that you interpret program terms as programs, and hopefully the definitional equality has something to do with the fact that on closed terms, you might have a step rule that looks like it. Okay? I mean, it's not a priori obvious that if you write down any formal system of equations and syntax, it may not have a computational model. You may have written down things where programs don't satisfy progress and preservation, right? We had in mind, based on the way we were thinking about pi and sigma, that we put in certain equations that happen to look like these. And so maybe, we've done our job well and it has a computational model. Okay, that's a very nice thing. For some perspectives, that's the defining thing that you might want a type theory to have. But another thing you can do with a formal type theory is look at other mathematical models. Okay, and this is what leads to the study of homotopy type theory. So the idea here is that we don't just have the model where these things that we call terms denote programs. We also have models in various mathematical settings. And then the thing that we can do that's really cool, for me at least, is that we can do constructions in those mathematical settings by writing down these terms. So it turns out that these rules for the identity type don't just apply in a setting where you're thinking of the identity type as being kind of proofs of equalities that don't have any structure to them. You can give models where you think of a P that has type x equals y as denoting some notion of morphism in a category from x to y. So each type then itself becomes a structure like a category where it internally has a notion of morphism on its elements. And then from these rules for the identity type, if you have a P and a Q that goes like that goes from y to z, then, well, in the syntax from transport, you can define composition of these morphisms, which is exactly going to be transitivity of these equalities, chaining this together with that. So you write in the syntax what looks like, hey, I'm proving that propositional equality, the type of equalities, is a transitive relation. And it turns out to have structure that composes these things. And then if you have another thing here that goes from z to w, you can keep going here. So you can, for example, define a thing in syntax that says P composed Q composed R is the same in a sense as P composed Q composed R in that order. I write these as semicolons. Where this is a morphism that goes all the way from x to w in some type A. And so from this idea of the elimination rule for the identity type, you can denote an operation that shows that this operation of composing morphisms like this is in fact associative. Okay, so we're not just talking about a structure where things are morphisms, which are sort of like a set of morphisms or something like that, that we can compose like an equivalence relation that's transitive, we're talking about a structure where that composition satisfies some equations. And then you can go even further, and if you look at the two different ways to reassociate PQRS to PQRS, you can work it out that there's two different ways to kind of flip the parentheses that look kind of like this, then that commutes and so on. Okay, so like imagine flipping the parentheses by a bunch of individual operations. You can either first flip those and then flip those and get down there, or you can do the inner flip first and then do some more flips. Okay, so this is a structure that's called an infinity group that people study in certain mathematical settings, because it's like, if you know what a monoid is, which is a binary operation that's associative, it's like a higher dimensional analog of that, where you have a binary operation that's associative, that has composition, whose composition is associative, and then that associativity itself is coherent in this sense, and then that coherence is itself coherence in a different sense, and so on all the way up. And all of that all the way up turns out to follow just from this one axiom. Okay? So there's a very simple rule that generates a whole lot of structure. And so one thing you can do besides giving a computational model of dependent type theory as a formal system is you can use it to describe constructions in these settings where you have all of this higher structure that's sort of not really put in by directly writing it all out in its full gory detail. It gets quite complicated if you want to say this out in full detail. Instead, we have a nice axiom, a nice rule that generates all of it. Okay? And so one of the interesting things in homotopy type theory is looking at the interplay between these two kinds of perspectives. So you can have both a computational take on what these terms mean and also a mathematical take, interpreting them in mathematical settings like simplicial sets, which don't a priori have anything to do with computation. And you can think about how the two different kinds of models interact. So that's why I wanted to stress the distinction of judgmental equality is a formal system, right? You don't want to think of it a priori as it is computation or something like that. It's axioms about equality. Those axioms can be true in various mathematical settings, or they can become true under interpretation as programs. But if you think of it as syntax first, then you can get these many different interpretations going. And so then a lot of the work that I've done and other people have done is using type theory in order to prove statements in these mathematical models. Like, for example, you can define the circle as a type with an element and a loop, where the loop is an element of the identity type in the circle. And then you can prove a mathematical fact about the fundamental group of the circle happens to be isomorphic to the integers by writing down some equality types and the integer type, and then writing some maps between them in dependent type theory, and that constitutes your proof. Okay? So that's what I mean by using syntax to denote things. It's like you come up with a statement in the type theory that happens to mean something interesting in your mathematical model, and then by interpretation into that model, you've proved a fact. And the nice thing is that, I was trying to explain this last night to someone, like a lot of the stuff you do sort of says more than what the statement in the type theory is, because there's a lot of extra structure that gets carried along for free that you don't write out by hand, that you would write out by hand if you were doing it in kind of a more primitive way. Okay, that's kind of a high-level picture of what dependent types are at a very basic level, and then where you can go with them. And we'll see different places that you can go with them in terms of talking about them as behavioral types for specifying programs this afternoon, and talking about them more as formal types for structuring programs in Edwin's course as the week goes on. Okay, thanks.